In the Pacific, the surface is becoming a death trap. The ocean, once a vast and concealing space, is no longer a place to hide. Modern satellites do not only see ships on the surface, they can track every movement with precision, detect the heat left behind in the water, and follow the wakes stretching behind vessels from orbit. That means the ocean surface is becoming transparent. No ship, no floating object can easily escape observation. Anything that floats can be found, tracked, and targeted much faster than before. So to survive, naval power is moving where radar cannot reach and light cannot follow. Commanders are descending below the surface, seeking the hidden layers of the ocean where detection becomes unreliable, into the deep ocean. But the deep ocean is not empty, and it is not uniform. It is layered, dynamic, and full of natural defenses. Today, we declassify the thermocline loophole, the physics of the shadow zone that can help an 80-ton underwater machine vanish from advanced sonar. Chapter 1. The sonar lens. Sonar works on a simple idea. Send sound into the water, then listen for the echo. If the sound reaches the target and bounces back, you can detect what is there. But the ocean breaks that simple rule. It does not behave like a uniform space. As you go deeper, temperature changes fast, and those changes directly affect how sound travels. One layer matters more than the others. It is called the thermocline. The thermocline is a layer where water temperature drops quickly with depth. And when sound hits that layer, it bends. It does not continue in a straight line. This is called refraction. If that sounds abstract, think of a straw in a glass of water. The straw looks bent because light changes direction. In the ocean, sound does something similar. But here, the scale is much larger. The entire ocean becomes a medium that can redirect sound. The thermocline acts like a giant underwater lens. It bends sonar away from the target. It can push sound upward or redirect it away entirely, and that creates a shadow zone. A region where surface sonar becomes weak, distorted, or blind. A region where something can be present but remain undetected. Chapter 2. The Acoustic Labyrinth. This changes the battle completely. A ship on the surface may think it is scanning the water below, but the sound may already be bending away. What looks like full coverage can already be a blind search. That means the ocean is not an open box. It is not a simple space where signals move in straight lines. It behaves like a layered environment, constantly shaping how sound travels. It is an acoustic labyrinth, a space where sound paths curve, split, and sometimes never return. A place where physics can hide a machine better than armor can. And that is why the deep ocean matters more every year. Because when the surface becomes easier to track, the value of the underwater blind zone rises sharply. What cannot be hidden above water can still be hidden below it. The ocean is not only deep, it is selective. It lets some sound through, bends some away, and traps some within layers. This turns detection into a geometry problem. Not just distance, but angle, depth, and position. A target may be close and still remain invisible. Chapter 3. The 80-ton ghost. To exploit this loophole, engineers are building a new kind of machine, the Orca XLUUV. XLUUV stands for Extra Large Unmanned Undersea Vehicle. This is not a toy drone. It is a 26-meter autonomous submarine with an 80-ton displacement. That is the size of a small submarine capable of carrying heavy equipment, yet it operates without a crew. Think of it as an underwater robot built to disappear, wait, and act. It is designed for stealth and patience rather than speed. Its entire structure is optimized to blend into the shadow zone and remain unseen. Powered by a hybrid diesel-electric system, it can remain underwater for long periods. This allows it to patrol silently, conserving energy while staying hidden from sonar detection. It can loiter near the sea floor, remaining motionless for hours or even days, waiting for the right opportunity to act. and it can carry modular payload bays for different missions. Whether for surveillance, intelligence gathering, or tactical operations, these payloads can be configured according to mission needs. In simple terms, this is an autonomous hammer that can sit silently in the shadow zone while the mothership is thousands of miles away, ready to execute its mission without being detected. Chapter 4. Navigation without sight. But the hardest part is not pressure, it is logic. Surviving underwater is only one challenge. The real test is knowing where you are when there is no outside guidance. Underwater, there is no normal GPS. There is no fast data link. There is no constant human control. Signals from above cannot reach deep, and remote instructions arrive slowly, if at all. So the vehicle must work out where it is by tracking its own movement. That is called inertial navigation. An inertial navigation system measures motion, direction, and vibration to estimate position over time. It continuously monitors every tilt, turn, and shift of the hull. Over time, it calculates its location based purely on its own movement. In simple terms, the drone keeps a running record of every turn and every movement of its own hull. Then it listens, not for voices or words, for signatures. This is called acoustic fingerprinting. Every object in the water has a distinct sound. A whale sounds different from a merchant ship. A merchant ship sounds different from a destroyer. The machine has to recognize those patterns and make limited decisions without talking back to a human operator. It must interpret the world silently, act independently, and navigate accurately. That is the real engineering challenge. Not surviving underwater. Thinking underwater. The side that masters the shadow zone gains an enormous advantage. Control over these unseen layers transforms naval strategy completely. Because in modern warfare, you cannot fight what the ocean helps you hide. A vessel or drone hidden in the shadow zone is effectively invisible, untouchable, and able to strike or observe without detection. This roadmap started in Arctic ice, where extreme conditions first challenged traditional tracking methods. Then it moved to the launch physics of carrier decks, exploring how machines and forces interact in controlled but high-stakes environments. Now it descends into the Pacific Deep, where natural layers, temperature shifts, and the vastness of the ocean create strategic blind spots. As the surface becomes easier to track, the real competition is moving below it, not into darkness, into physics. Mastery here defines tactical superiority. The side that masters the shadow zone gains an enormous advantage, because in modern warfare, you cannot fight what the ocean helps you hide. And that is why this layer matters, but this is only one part of the system. Because the same physics that hides machines underwater is connected to how we launch them, control them, and deploy them across the battlefield. If you want to understand how this system connects, watch the next breakdown. Subscribe to Modern Classified Global for more. And watch how aircraft carriers launch 80,000 pounds in 3 seconds. Dismissed.